Good evening, everybody. Welcome to the second day of ATAL FDP on Secure and Intelligent Systems on Chip. So today we have two very interesting talks. So we will wait for a couple of minutes more before starting today's activity. Welcome, Kala. So we'll wait for 2 more minutes.
Yeah, sure. Thank you.
Okay. Okay, good evening, everyone. Today we'll start the activity. Today's first session, and it's my privilege to introduce Dr. Kala. Yes, she is an assistant professor at Indian Institute of Information and Technology, Kottayam, and is leading the Integrated Circuits and Systems Research Group, I2CS, where here she is taking numerous initiatives for research and development projects in industry and other agencies, and is leading the product development and product and system development group there. She has been a visiting researcher at Ruhr University, Bochum, Germany since 2023. She has received her PhD degree from Cochin University of Science and Technology in 2020. Her MS by research degree is from Center for Nanoscience and Engineering, Indian Institute of Science, Bangalore. She is the recipient of prestigious Women Involvement in Science and Engineering Research Award from Indo-German Science and Technology Center, established by DST, Government of India, and Federal Ministry of Education and Research. Her research, teaching, and industry collaboration activities include digital system design, system on chip design, VLSI and FPGA-based system design, computer architecture, and hardware accelerators for digital signal processing algorithms. He has published many research papers in this area in reputed journals and presented papers and received various awards in leading conferences like VLSID, ICSCC, IRTM, etc. She has guided several undergraduate projects and supervised several PhD students in these domains. It's my privilege to invite you to this FDP. Welcome, Kala. I hope the participants have a very informative and interesting session with you. Over to you, Kala.
Thank you, Dr. Tripti, for the nice introduction. Good evening to all participants of FDP. And thank you, Dr. Nalesh, for inviting me to deliver this talk. So I'll share my slides. So I have shared my slides. Are the slides visible?
Yes, Dr. Kala, it's visible.
Okay, thank you. First, we will start with a small introduction to artificial intelligence and machine learning. And in this section, so I'll quickly go through this section. In this section, because we have you have already listened to the presentations yesterday, where an introduction to artificial neurons, biological neurons have been presented by Dr. Nalesh. So in this section, we'll just quickly see the biological and artificial neurons, and then we'll have an introduction to deep learning. So during yesterday's presentation, again, you might have listened to brain-inspired computing. So basically, this brain-inspired computing, or BIC, BIC, it refers to computational models, algorithms, or hardware systems, and they are inspired from the how this human brain processes the information. And instead of following the traditional architectures, they mimic biological neurons. This is what we have seen yesterday. And neurons, as you know, they are the fundamental processing units of brain. The neurons will receive signals, they process that, and then they'll send output to the next neuron. So basically, the biological neuron consists of dendrites, then cell body will be there, then axons, synapses. These are the components of biological neuron. And artificial neuron, as you know, it's a mathematical abstraction of this biological neuron. Or we also call it as perceptron, or sometimes it is also called nodes. So basically, this neuron consists of artificial neurons, they consist of inputs denoted as x1, x2, x3, etc. Then we have weights, w1, w2, etc. Then you have bias denoted by B, and then we have activation functions. And these activation functions, they'll decide whether the neuron has to fire. And again, here you can see spiking network, spiking computing. So basically, neurons receive these electrical spikes from at their dendrites, and then they will have this all these signals combined in the cell body, or call it as soma. And then these signals, if this if these combined signals they exceed a threshold value, then neuron will fire, or neuron will fire, or neuron fires this spike. And then this spike will travel through traverse through the axons, and it reaches synapse. That's what this diagram shows. And then this neurotransmitters, then this will affect the next neuron. This is how the spiking process goes on. And then we have another topic, linear classification. So before we come to deep neural networks, we can see the simple linear classification, what it is. So basically, this linear classification, it is a fundamental machine learning technique. And here the objective or the goal is to separate data into different classes using a decision boundary, and this boundary will be a linear decision boundary. So for example, the boundary can be a straight line or a plane. in 2-dimensional it can be straight line, or in 3-dimensional it can be a plane, like that, or in higher dimensions it will be hyperplanes. And then we have this linear classifiers. They will decide the class of this data by using a linear function. That's what you see in this expression, f of x w, that's equal to wx plus b. So that's a linear function. So output is equal to w1 x1 plus w2 x2 plus etc. plus the bias b. That is a linear function. That's going to be linear function. And then the decision will be you will have a class 1 or 0. 1 if you have this wx linear function greater than or equal to 0, otherwise it will be 0. So that is the linear classification. And the simplest linear classifier is a perceptron. And another linear classifier is, we have heard about logistic regressions. Those are also linear classifiers. Why these are linear? Because you have this linear combination of the features. And then your decision boundary is also linear. In the next slide, you can see an example here. You have this 4 pixels, and they are stretched into column vector. You have this weights multiplied with the pixels and then added the bias, you get classes there. So this is an example of linear classification. And linear classification, it works very well if your classes, if the classes are linearly separable. But when the classes are non-linearly separable, you cannot use linear classification. That is a limitation. And when your features are having a linear relationship, then this works well. Otherwise, this will not work for classification. That's what this diagram shows. You cannot have a line to separate the classes here. Now we will move on to deep neural networks or deep learning. So we'll revisit this neurons that we have seen in the previous slide. So we have 3 steps to follow here for this neuron computations. First one is you have the weighted sum. Then the next is you have an activation function. So your weighted sum is wx plus b. That is your weighted sum, and then you have the activation function, function f of z or whatever you call it. Yeah. And this activation functions, some of the examples of activation functions which are very commonly used are, you might have heard about sigmoid functions, ReLU, TANH, then what is it? Softmax. Those are activation functions. Basically, this non-linearity in the deep neural networks, they are introduced through this non-linear activation functions. And this deep neural networks will get the capability to learn this complex networks through this non-linear functions. So these functions are introducing non-linearity to the data, input data, and this is essential for the network to learn complex patterns. And apart from this ReLU sigmoid, there are some more functions like swish, mish. Those are also used as activation functions. So what they will do is that they'll break that linearity that we have seen in the previous slides. So basically, this non-linearity is what which allows this deep neural networks or deep learning models to learn this complex networks or complex patterns, and then almost all the real world problems are non-linear in nature. So this diagram shows deep learning network. So neural networks basically which are having more than 3 layers, they fall into the domain of deep learning. So we will come to the structures later. Some of the popular deep neural networks are fully connected networks or the conventional artificial neural network. or a multi-layer perceptron, we call it as. And then we have CNNs, very popular neural network, convolutional neural networks. And then there is something called recurrent neural network, then LSTM, long short-term memory. There are several different kind of neural networks already been studied. Now coming to another term, training and inference. So basically, this training and inference, these are the two main two main phases of how this machine learning or deep learning model operates on. So training is the learning phase. So it is a process where the model own outputs already, or you can call it labels. Am I audible?
Now you are audible. In between, there was a slight gap.
Okay. Okay. So training is, so what I was telling is about training and inference. So, in training, during training, this model will learn these patterns from the input data, and then it makes predictions. Basically, it makes some predictions, and then we have this actual data also and the predicted data. So you find out the loss. You calculate the loss. It's the difference between this prediction and this actual output. And then model will do an updation or updates its parameters. These parameters, in the sense, they are the weights and the biases. And the goal is to reduce the loss. And that is the training process. And now this training will take multiple hours or multiple days. So high computing machines are required, like GPUs or TPUs are required for performing this training. And then next is the inference. So inference, that is the second phase where you have this trained model, and you use that trained model to get the predictions on some new data. You have this trained model available with you with the available data, and now you give new unseen data or new data to get the predictions. So so here what happens is that you are giving a new input to that model, and then the model will perform what is called a forward computation, and then predict the outputs. And comparatively, inference is much faster than training. And here weight updation will not happen. No weight updation is happening during the inference. So this is about training and inference. Now, coming to data sets. So before that, there are three components that enable the breakthrough of deep learning. So during a period of 2010 to 2015, there was a breakthrough of deep learning, and it was possible through three major components. So one is computational power, then parallelism of for training, then availability of labeled data set. So availability of very powerful hardware, computational hardware like GPUs and TPUs have enabled the breakthrough. And with the help of GPUs have enabled very fast operations, fast parallel matrix operations, and training of very large neural networks. Instead of months, you could do that within a few days. And we have availability of labeled data sets also, which enable the breakthrough of deep learning. So why this data set mattered? Now, if you have more data, you can have more or better generalization, and then deeper networks can be trained. So, and another point is to add to this is algorithmic innovations. So we have a better neural network models and better architectures. Then we have good training techniques. All these have also contributed to advancements in deep learning. And then some of the examples for data sets are also given here. Very popular MNIST, CIPAT, and all these ImageNet, all these are very popular data sets. Now we will move on to some basic CNN models. So we have very popular models, LANET, ALEXNet, VGGNet. These are the very popular CNN models which have been used in, for research purposes and for real-time purposes also, implementations, real-time implementations also. So here, LANET is one of the earliest convolutional neural network architectures. These are used for handwritten digit recognition. So the data set that has been used is MNIST, as we have seen in the previous slide. Actually, the ideas that modern CNNs are using also start with the LANET. So we have convolutions, subsampling, and fully connected layers. This is a typical pattern for this convolutional neural network. So we will come to this mathematics in the next slides. So we have ALEXNet here. Next model is ALEXNet. As you can see, you have 5 convolutional layers, 3 fully connected layers, and then in between you have max pooling layers and normalization layers. So we will see each of these layers. And ALEXNet has 5 convolutional layers. So first convolutional layer, it uses 11 by 11 filter. The kernel size is 11 by 11. 11, of course, 11 by 11 is the kernel size, and the input image is 227 by 227 RGB. So you have 227 by 227 into 3. The input size is 227 by 227 into 3. Then we have 96 such filters applied to this image, input image. So we have 96 11 by 11 filters, and each applied at a stride of 4. The stride is 4 here. And how do you find out the output volume from the first convolutional layer? So it is input image size, that is 227 minus filter size, divided by 4 is the stride size plus 1. So you will get 55. So output, you will have 55 numbers there. Output volume size is 55. So you have 55 by 55, not 55 numbers, 55 by 55 is the size of the output feature feature map. So you have 55 by 55 and 96 such feature maps will be there. So 55 by 55 into 96 is the output volume from first convolutional layer. Now how will you find out the number of parameters in this layer? So parameters is found out using this expression. You have a filter size 11, so 11 by 11 into 3 RGB into 96 such filters are there. So you have 35k parameters from this first layer, in this first layer. So similarly, you can do this for each layer, given the filter size and the input image size and how many number of filters are there, or how many channels, how many channels are there in the filters or kernel channels. Then you can find out the parameters and output volume size. So next layer is the pool layer. So in pool layer, pooling layer, you have a 3 by 3 filter and stride is 2. So now you can find out what is the output volume size from after pooling layer. So that will be 55. 55 is the now the input feature size. So 55 minus filter size divided by stride plus 1. So you will get 27. So you have 27 by 27. You can see 27 by 27 there. Into again 96 numbers will be there. So similarly, you can find this for next convolutional layer also, next max pool layer also, and the upcoming layers also. So Similarly, for VGGNet also, you can find this out. VGGNet is the next after AlexNet. In 2012, AlexNet has been introduced, and then in 2014, VGGNet has been introduced. So we have VGG 16 and 19 with a different number of layers, 16 and 19 layers. And here you are using less kernel size is less when compared to AlexNet. And AlexNet, you were using 11 by 11 in the first layer, then 5 cross 5 in the second layer, and then 3 cross 3. Here it was 3 cross 3 alone. So, you can stack 3 cross 3 to get 7 by 7 convolutional layers also. Both will give the same receptive field. And you have, but you have some advantages here. Parameters, you can have a less number of parameters if you use the filter size. Now here mathematical calculations for finding out the parameters of each layer has been given as per the formula that we have discussed in the previous slide. For AlexNet, it is applicable to VGGNet also, and you can find out how many parameters are there in each layer and what is the number of computations also. So here we can see that convolutional layers, you have in red color you can see this many parameters are there in the convolutional layer. What is the memory utilization for convolutional layer? So total number of parameters in FC fully connected layers also, and then the memory that they are using, etc. is given in this slide. So it is obvious that computations are more in convolutional layers, and memory requirement is more in fully connected layers. From this computation, from these calculations, we will get to know that. So this has been introduced in yesterday's session itself. Computations, number of computations, and memory requirement, etc. for each neural network model. Now moving on to the next section, that is hardware accelerators for deep neural networks. So we have discussed so many algorithms in deep learning, neural networks, etc. So the software that has to be accelerated, it can be a convolutional neural network or a multi-layer perceptron, or it can be a graph neural networks, it can be adversarial networks, it can be a transformer model, or RNN, anything. So and typically this hardware acceleration is performed during the inference of these networks. We have seen inference and training. So during inference, we perform this hardware acceleration. And what hardware? So before that, this hardware acceleration it typically refers to using any specialized hardware for performing some computational, specific computational tasks faster and more efficiently than performing on a general purpose processor or CPU. So instead of running everything on the CPU, some operations, especially some operations which are computationally intensive, that can be offloaded to the custom hardware units. So that is called hardware acceleration. And what kind of hardware we can use? Typically, von Neumann architectures we have seen in the previous yesterday's session probably. That is a conventional architecture, and unconventional computation, unconventional computing techniques like neuromorphic architectures are also used for implementing AI on hardware. So that is a recent advancement. Unconventional hardware, that is a recent advancement. You may have listened to that in the yesterday's session. Moving on to specialized hardwares. So why we require specialized hardware for AI, especially for AI, because modern AI or deep learning it demands massive computation and high parallelism, also high bandwidth requirement. And this traditional computing units, traditional like CPUs or GPPs, they may not be able to provide this efficiently, like the bandwidth and the high memory requirement or massive computational requirements cannot be met uh, with the conventional CPUs or GPPs. So AI requires huge amount of computation, and deep learning or AI, you have millions or billions of parameters involving in the computations, and data is huge. Data is huge, and then the computations are matrix operations. So you have repeated, uh, matrix multiplications or computations there, and lot of or millions of or billions of math units will be required, or multiply and accumulate units are required, or multiply and accumulate operations are required for performing A. And the CPU or the general purpose computing machines, they are specifically built for sequential tasks, or they are very slow for doing this AI jobs. And so you have specialized hardware like GPUs, and GPUs, you have FPGAs, ASIC, which will accelerate this matrix multiplication, which is a major component in any AI algorithms, ML algorithms, or deep learning algorithms. And then, or the specialized hardware can accelerate convolution operations in the convolutional neural network, and it can support the high memory bandwidth requirement for AI application. Also, these accelerators, they will have HBMs, what is it? High bandwidth memory. They will have high bandwidth memory and on-chip SRAM, which can support the memory requirements of, to some extent, they can support the memory requirements of AI applications. And another important point here is energy. So, specialized, if you have specialized ICs or specialized chips, they can then perform these operations, matrix operations or computations or convolution operations that may be very much lower energy comparatively. So this is why you have requirement for a specialized hardware. And the need for speed, and for real-time applications. So many of the real-time applications will require instantaneous processing. For example, you have self-driving cars, or robotic or medical devices, etc. So some the CPUs or general purpose machines processors, they may not be able to meet the latency requirement. So in that case, accelerators can be used to ensure that the inference happens within the time frame. So that is one reason where accelerators give an advantage. And we have huge, AI demands huge computation. You have more data, big data, you have bigger models, and so your need for computation is also high there. So the summary of whatever we have discussed so far is given in this slide. So we have hardware accelerators for getting high performance inference with good energy efficiency and less cost. And typically training will be done using GPUs and all, and inference will be performed on a specialized hardware. Now, so here you see a deep neural network, and the key operations in a deep neural network is matrix multiplication, dense matrix multiplication, as you know. And this, so you have weight matrix and input multiplied with the weight matrix. This is what we have seen in the neuron, the slide for the neuron. And this operation will be repeated for every layer. Each layer, this is repeated. Dense matrix multiplication. And then Here, um, for optimizations or for better usage of computational units and memory, what we can do is we can reuse the weights of filter weights, coefficients, input coefficients, etc. can be reused to get better efficiency. That is one technique to improve the performance of your system. And we can use the batching also for improving the efficiency. But in the real time operations, we may not be able to use batching, and we have to make use of exploit the sparsity available in the weights. And in DNN, you have a lot of parallelism available there within the layer itself. The layers will be computed one after the other, but within a layer, you can have good amount of parallelism, and you can make use, exploit that parallelism. So the layers that are dependent, layers are dependent, but within the layer, you can have parallelism which can be exploited. And now another way to improve the efficiency is reducing the precision. So once you do quantization, you can have better storage, you can reduce the storage, you can have better energy efficiency and improve the performance. And all this can be done with the with a given accuracy. It means if the accuracy is not affecting too much, we can have good quantization deployed on the system. So the precision, you can have quantization in the weights. So here it all depends on how much accuracy do we need for that particular application, for that computation. What is your requirement? Based on that, you can have a quantization. So different kind of quantization is listed here. Floating points, 32, 16, fixed point, integer, etc. So based on the accuracy requirement, you can have better precision deployed on the system. You can also use mixed precisions. So for weights, you can have some precision. So for activations, you can have another precision, and then for MAC-units accumulations, you can have another precision. So these are also possible. Mixed precision is also possible for improving the efficiency of the accelerator. So reducing this precision, it can save the memory, bandwidth, power, and give good performance for the system. Now, another technique for improving the system performance is using local memory. So how much energy you can save here when you go for local memory, then on-chip SRAM, and then when you go for DDR is shown in this diagram. So it is always better to use local memories for as far as possible for improving the efficiency. Now coming to algorithms, the major computational component in convolutional neural networks are convolution operations. So convolutional operations, they can be performed using different algorithms. So choosing an algorithm is very critical when you do the implementations on hardware. There are different ways in which we can implement convolution operations. So one of that is, one is the conventional technique in which you have this sliding window operation. Another technique is using fast Fourier transform, FFTs. So here, what is done is you have this input image and the kernel. So you perform Fourier transform on the input image as well as the kernels, and then you can take the inverse of the output, inverse Fourier transform to get the output. So typically, when you do this Fourier transform, you have a multiplication there. In real time, in typical examples, you will have a small kernel size and a larger image size. So you will have to do what is that? The sizes will not match. So for the multiplications, so for larger image size and smaller kernel size, fast Fourier transform technique may not be effective, but for smaller image size and for smaller filter size, this can be used because you have to match the size of the multiplication. So for so conventional, so FFT convolution will give you much advantages on computations for smaller filters and for smaller image sizes when compared to the conventional technique for convolution. So here you have a comparison of the direct or the conventional convolution, how many operations, computational complexity of conventional convolution and FFT convolution. So you will have a savings of which is proportional to k square, where k is the filter size. When you go for FFT convolution, and this is good for a smaller image size, or if you go for a larger filter, this will be good. So there are several works published in 2017 and 18 for optimizing this FFT based convolutions. And another algorithm was Vinograd minimal filtering for convolution. So here, this Vinograd minimal filtering is a very popular algorithm, and this algorithm can also be used for performing the convolution operations. So here, you have an input feature map. You can divide that into tiles, and then you have the kernel also. You can perform convolution operations in the tiles, or on the tiles, on different tiles. So there are expressions for finding out the tile size, and suitable tile size need to be found out in order to get better results. So there are some computations that need to be performed on the input. The input has to be transformed into some form, and filter also needs to be transformed into another format, and you will get an output. And this, after performing this Vinograd minimal filtering, you will get an output, and this output also needs to be converted into some other transformed format. So there are some computations happening during this Vinograd minimal filtering algorithm computation for convolutions. So when you compare with the conventional convolutions, this Vinograd minimal filtering algorithms, they will take minimum number of multiplications when compared to the conventional, but a little bit more additions, which is desired, which is acceptable when you consider the computational complexity. So you have a kernel of R cross R size, and you have output. After Vinograd, you are getting an output. The output size is M by M. So we usually give the notation of M comma R for the Vinograd tile. So that M is the output. if we write 2f of 2 comma 3 means that 2 is the output size and 3 is the kernel size. So based on the output size and the kernel size, you can find out what will be the input size. This is how the tiling notation is given. So in this example, f2, 3 is written. So 2 is the tile size. So in this diagram, we can see Z1, Z2, Z3. So that Z1 is 2. That is 2 cross 2 is the tile size there. So R is the kernel. Orange color denotes the kernel. So R is the kernel size. So kernel is 3. It means 3 cross 3 is the kernel size, and input is Z1. Y1 is the output. So output comma kernel is what you write there, and you can find out what is the input tiles, what should be the input tile size that gives this particular output. That is how it is written. When you compare this Vinograd with the conventional convolutions, the complexity, the ratio of the complexity is given as m square r square divided by m plus 1 minus 1 r square. So this m denotes the output and r denotes the kernel. And different tile sizes can be used to implement compute convolutions. 2, 2, 2, 3, 3, 3, 4, 3, 6, 3. These are the very commonly used tile sizes. And we have done some experiments with different tile sizes and what is execution time. If you take different tile sizes for all the 3 algorithms, the direct convolution or the conventional convolution, then FFT based convolution and Vinograd convolution, if you use 3 convolution techniques for different tile sizes, what will be the execution time? So experiments have been done to see that, to choose the convolution technique which will be most suitable or apt for real-time implementations. Moving on to hardware accelerators. So far we were discussing about the fast algorithms that we can use for implementing this convolution operations. You can have conventional convolutions, you can have FFT based convolution, you can have Vinograd based convolution. All these algorithms have been explored. Now moving on to the accelerator. Direct convolution or the conventional convolution. So these are suited for, when the kernel size is very large. For example, you have AICTE, which uses 11 by 11. Then the second layer uses 7 by 7. You have 5 by 5. So then you have 3 by 3. So the kernel sizes are 11 by 11 itself is a very large kernel size. But when we move on to FFT, your kernel size also should be large, your image size also should be large. Otherwise, you should have a match of the size, kernel size and image size. Then typically suitable for same sizes. Then next you have Vinograd minimal filtering. So there, for small kernel sizes, typically for 3 by 3 or less, Vinograd minimal filtering works well. And we have seen that after going through many research papers, we have seen that researchers were using architectures where you have a dedicated processing elements for Vinograd convolution alone. But then the problem is that you have convolution layers and FC layers, fully connected layers also. So fully connected layers will require another separate processing elements, and convolution layers will require separate processing elements, because Vinograd convolution will perform for convolution layers. So what happens is you have underutilization of resources here. And if you take AICTE as a case study, the AICTE will have 11 by 11 filter and 3 by 3 filters also. So you have a mixture of large kernel size and small kernel size. So if we can combine this direct convolution, which is suitable for large kernel size, with the Vinograd convolution, which is suitable for 3 by 3 or less kernel size, and then you have fully connected layers also. If all this can be computed using the same processing elements, or you will have a lot of resource savings in the hardware. So in this regard, if we look into the possible accelerators, we have seen that this Vinograd algorithm, this can be computed using general element based matrix multipliers also, or that is called a GEM. General element based matrix multipliers can be used to perform this Vinograd minimal filtering algorithm. So there was one high performance GEM accelerator published in 2018. So that accelerator, we have taken that accelerator to perform this Vinograd minimal filtering algorithm also. So in that case, what we can do is this GEM can be used to perform the direct convolutions also, and which is conventional convolution, and also Vinograd convolution. So a high performance GEM accelerator will do both the convolutional operations and FC operations. So all layers can be accelerated in then using that GEM accelerator. And another technique to improve the performance is blocking. So blocking technique will improve the performance of the system. So we have done blocking technique in the GEM algorithm that has been presented in ISCAS 2018. So blocking will improve the BRAM utilization, and it will improve the bandwidth also. So we will get a good performance there. So this blocking technique has been used in Vinograd minimal filtering algorithm, which uses the GEM accelerator. So this is the block multiplication that we have used. So you have rows and columns as blocks, and then multiplication has been done, which improves the performance. So this is a well-known technique for improving the performance. So here in the previous slides, we have seen that we have input data. That input data has to be transformed and then into another format. And you have a filter also needs to be transformed into another format. So this transformed input and the transformed filter, they are getting multiplied, and the multiplier that has been used here is the blocked multiplier. Blocking technique is used in the multiplier there. So you will get an output, and this output will be transformed. So that is a technique. Transformation is a technique used in Vinograd computations. So this is the blocked Vinograd filtering algorithm that has been used to perform the convolution operations as well as GEM operations, basically. So a unified Vinograd and GEM architecture has been developed in order to accelerate the CNNs like ALEXNet and VGGNet. So for ALEXNet, we for the first layer, we can use direct convolution of the Vinograd is not required for first layer. So in that case, you don't have to do any transformations in the input and the kernel. So that data, that red color inside that box, you have the data transform unit and output transform unit. So those transformations are not required. So you can bypass it. So that blue colors will show the GEM data path where you are bypassing that Vinograd operations. And the red color, it shows the Vinograd. So for other layers, you can use the Vinograd operation. Only for layers like first layer of ALEXNet, you can use GEM data path. So this is how, and they have processing element arrays which perform the GEM. The GEM operations have been done using this processing element arrays. So there are several experiments have been done to find out the size of the arrays, PE arrays, optimal size of the PE arrays. This is unified Vinograd GEM architecture, and details of the architecture is available in the TVLSI paper. So the experiments have been done for various tile sizes. for a particular model. So we have taken AlexNet and AlexNet, VGNet, and VGG16 and ResNet 18. So for 3 models, we have done these experiments with different tile sizes, with different tile sizes. And comparison have been done with the existing works, and it has shown comparable or a good performance or comparable performance with comparable resource utilization. And the results are also available in the paper. Next, moving on to that. So the operations that we have done so far, they are dense operations, dense matrix operations, and when we do techniques like pruning and all, you get a sparse matrix and sparse. So in that case, dense operations will not work. So sparse operations need to be done in the accelerator. So this work, sparse CNN accelerator. So this has been done by my PhD student, Noble. The rest of the slides are his work. So basically, sparse matrix is a matrix where most of the elements are 0. So you can see the difference. It's trivial here. You have a dense matrix and you have a sparse matrix. Only a few elements are there in the sparse. So after pruning, you will get basically you will get a sparse matrix. So the operations, sparse computations are different from that of the dense operations that we have seen so far. Now, sparse matrices are basically you have this sparse matrices seen in almost all the deep learning or neural networks, then social networks, everywhere. You have many examples where you see sparse operations or sparse operations with sparse matrices. Now, there are different storage formats for sparse matrices. Very commonly used, very popular storage formats are a coordinate format, CO. Then I'll just go through the different formats. So you have a coordinate formats, then you have a compressed sparse row format, then we have a compressed sparse column format. So there are techniques in which how you convert this dense matrices. So shown in the left, you have dense matrices. How do you convert into CSR, compressed sparse row, compressed sparse column matrices, and then there are few more storage formats like blocked CSR and delta CSR. All these are available in the literature. So different sparse storage formats are available. And my PhD student has been working on finding out an efficient sparse matrix storage format and performing the computations, finding out the compression, different compressions, an efficient compression technique for this sparse matrices, and then utilizing that sparse. Then he has moved on to proposing a multiplier accelerator for a sparse matrix multiplication, and then using that develop a sparse neural network. That was the complete picture. So we started with the sparse matrix multiplication accelerator, which has been named as MOSCON, Modified Outer Space Product-Based Sparse Matrix Accelerator with the configurable type. So this outer space product, it is already available in literature with the GPU implementation. So we have done modifications on the outer space product and implemented it on the hardware with the tiling techniques, and results and the architecture details are available in VLSI design paper. And this paper, this work was one of the best paper candidate during 2023. So tiling technique is the highlight of this multiplier accelerator. Then we have moved on to compression techniques, different compression techniques for sparse, which our motivation was to handle irregular sparsity efficiently and reduce the memory consumption, or reduce the memory or storage. Reduce the storage was the motivation for this, so that you get a better performance sparse neural network. So, traditional storage formats, they were using high memory. Utilization was very high. So, we have come up with a new storage format, sparse storage format, which we have called as a memory efficient a delta CSR format. So, delta CSR was already available in literature. So, modifications have been done in developing the MDCSR compression format. And the feature of this format is that when compared to other formats like CSR and delta CSR, etc., coordinate formats, COO, etc., we have a large amount of memory savings for storing the sparse matrices. So the results have been published in IIIT embedded system letters. So what we have done is matrix storage, matrices, sparse matrices in CSR format. They have been converted into MDCSR compressed format. So we have developed or proposed an architecture for this conversion, and the results have been very favorable to us. So the sparsity, you can see this graph, what is the percentage improvement when you compare with the CSR and delta CSR, the existing techniques. For various sparsity levels, what is the percentage improvement? So that has been shown here, and the details are available in very recent paper, IIIT Embedded System Letters paper. And then using this format, using this compression techniques, we have developed a sparse neural network and has been deployed on hardware, which is a FPGA, microchip FPGA, and that those slides are not presented here because it is under review, and once it is published, it will be available publicly. So with this, I am winding up the session. So after MDCSR compression, it has been taken to a sparse neural network for hardware deployment. So this is the work of my PhD student, Noble, who is about to complete his degree. So a small note about our research lab. So I am leading a research lab at IIIT Kottayam, and we do focus on certain areas in VLSI and embedded systems. One is the hardware accelerators. Apart from this, we also focus on approximate computing. Several undergraduate projects and PhD thesis is going on in this area also, approximate computing, then neuromorphic architecture and hardware security. So here we focus on post-quantum cryptographic architectures. And in edge computing, we focus on implementations, machine learning implementations on edge devices. So these are some of the areas where we are looking into. And I am open for any collaborations also. So this work,
Thank you.
the sparse neural network accelerator, that work, it is supported by IGSTC, Indo-German Science and Technology Center, through WISER program. And the collaborators for this work are Dr. Akash Kumar, Rural University Boham, Dr. Salim, Rural University Boham, and Dr. Nalesh, Kusat Kochi, and my PhD students, Noble and Aparna Nair. She is also working in this area. And I also thank all my research scholars and my undergraduate students who have been putting their effort on the topics that has been mentioned here. So with that, I'm winding up the presentations.
Thank you, Dr. Kala. If there are any questions, we are open to questions. Okay, thank you, Dr. Kala, for this excellent presentation. You covered the basics and then talked about how you can accelerate deep learning networks, CNN particularly, and various methods were pointed out, and then presented work on how efficient implementations of accelerator can be developed by choosing fast algorithms and then you exploiting sparsity. So thank you, Dr. Kala. I hope those attending participants working in this area would have got an insight on if they plan to work in this area. And thank you, Dr. Kala. So thank you very much for this excellent presentation.
Thank you so much.
So,
thank you so much for inviting me for the session. So can I leave now?
Yes. So thank you, Dr. Kala. Okay,